Hello, in this video I'd like to talk about the closure properties of the regular languages. And this is the same notion of closure that I was talking about in the monoids video, the idea that if we take elements of a collection and combine them together in a particular way, that we get a new element of the collection. In this case, I'm interested in taking two regular languages and combining them together in a particular way to get a new regular language. And in fact, some of the operations we're going to be talking about turn the set of regular languages into a monoid. One of the really nice things about the regular languages is that there are so many operations that they are closed under, that there are so many things that we can do with regular languages and stay within the world of regular languages without having to go into some larger class of languages. And this is something that's very special about the regular languages. It's not something that you get with every single different type of language that you get associated to different types of computation, right? We can talk about finite state automata, which correspond to regular languages, and then there's other notions of computation, right? There's a slightly more advanced thing called a pushdown automaton. There's various ways of turning Turing machines into languages, and each of those defines a type of language. And some of those types of languages, even though we still study them, aren't nearly as exciting because they aren't closed under all of the different things that the regular languages are closed under. So, what sorts of closure properties do the regular languages have? Well, if we think back to the regular expressions video, there we showed that the regular languages are closed under union. If we take two regular languages and take their union, we get another regular language. And this is really easy to see from the perspective of regular expressions. If we have two regular languages given by two separate regular expressions, we can construct a regular expression for their union just by taking the two regular expressions and putting the union symbol, the vertical bar, in between those regular expressions, and now we have a regular expression for the union of those two languages. And one of the things that I'd like to stress in this video is that different perspectives on the regular languages are going to make these closure properties either much more or much less obvious. For instance, it's not obvious to me if I have two regular expressions defining two regular languages, how I could construct a regular expression defining the intersection of those two languages. That is, if I have two regular expressions, how do I find a regular expression for all of the words that satisfy both of these regular expressions? Not just one, because that's the union, but both of them. It's not clear. On the other hand, when we think of this from the perspective of finite memory machines, it winds up being really easy. Suppose I have two deterministic finite state automata here. I have my input keyboards, and they have different transition functions. So there's different things going on inside these machines, and we want to find what words will, when we enter them into both machines, make both of these machines accept. Well, all we need to do is merge the two machines. We take our input and feed it in simultaneously to both of our two machines, and then we simply take the two indicator lights, and if both of the indicator lights are on, then we turn on an indicator light for the whole machine. This gives us a single finite memory machine which determines whether or not the word that we type in will make both of these individual finite state automata accept. This perspective also gives us a really good intuition for if we want to make this proof a little bit more formal. Suppose that our first language, L1, is given by one finite state automata with set of states Q1, initial state Q0, 1, transition function delta 1, and set of final states F1, and language L2 is given by those things with an index of 2. Then the intersection of the two languages Well, in order to produce a machine that recognizes the intersection of these two languages, we're going to want a machine whose states are a pair, a state of the first machine and a state of the second machine. So here I use the Cartesian cross product notation to just indicate the set of all pairs of one state from Q1 and one state from Q2. One state of our first machine and one state from our second machine. And the start state of this system is going to be, well, it's going to be the start state of the first machine, comma, the start state of the second machine. And then I will define on a separate line the transition function and the set of final states, because I've run out of room. In order to update the state of this system, so suppose that this system is in the state S1, comma S2. So the first machine is in state S1 and the second machine is in S2, and we read a character C. Well, what's going to happen? We're going to feed the character C into the first machine and into the second machine, and so the resulting state of the system is just the pair of what we get when we update the first machine, which is currently in state S1, by the character C, and then what happens if we update the second machine, which is currently in state 2, by the character C. And so this defines our update, our transition function for this particular combination machine. And then finally, the set of final states is going to be the set of pairs of states that make both indicator lights light up. So in particular, it's just going to be the set of all pairs S1, S2, such that S1 is an accept state of the first automaton, and S2 is an accept state of the second automaton. And we could just write this as F1 cross F2 using, again, the Cartesian cross product notation, but it's more clear that this is the thing that we're going for if you read it out like this. So, given finite state automata for two languages, we were able to produce a deterministic finite state automaton for the intersection of the two languages, thereby proving that the set of regular languages is closed under intersection. Another really important closure property of the regular languages is that if we take a regular language and we complement it, that is, we take the set of all words that are not in that language, then that new language is also going to be regular. And this is really obvious to see if we think about this again from the perspective of deterministic finite state automata. We simply switch the accept and not accept states, and that gives us an automaton that accepts all of the words that were not accepted by the original automaton. But I think the simplicity of this demonstration really hides the difficulty of getting things to be closed under complementation. If we think about closure under complementation from the perspective of, say, regular expressions, it's not obvious at all that if I have a regular expression that I can produce a regular expression for all of the words that don't match the first regular expression. And then if we have a non-deterministic finite state automaton, our construction for deterministic finite state automata actually isn't going to work. Recall that what it means to be accepted by a non-deterministic finite state automaton is that there is some path from a start state to an accept state, following edges labeled by the characters of this word in order. If we flip that around, that's saying that there isn't a path from a start state to an accept state, which is very different from saying that there is a path from a start state to a not accept state. So it's not obvious at all that we can turn this into something that corresponds to being recognized by a non-deterministic finite state automaton. In fact, the construction that we have to perform is exactly the power set construction that we used in the first place to prove that non-deterministic finite state automata were expressively equivalent to deterministic finite state automata. Indeed, many times when you want to show that a particular representation of the regular languages is closed under a certain operation and it's not obvious, you have to do the translation to a perspective on the regular languages where it is obvious, and then do the translation back. And indeed, there are tons of different classes of languages out there that correspond to lots of different notions of computation where it's not the case that we have closure under complementation. It's actually fairly rare to get closure under complementation. And when we extend the notion of automata in other ways, which I'll talk about in a separate series of videos, the proofs of closure under complementation wind up getting way more complicated, to the point where closure under complementation actually winds up being the hardest thing to prove. So while for regular languages, proving closure under complementation is fairly easy, we can just look at the deterministic finite state automata, we should not take closure under complementation for granted. Another thing that's fun to think about is closure under reversal. So if we take a language and we reverse it, that's just the same as reversing all of the individual words within that language. And from some perspectives, this is totally obvious. If I have a regular expression and I reverse it, and move the stars appropriately, I wind up getting a regular expression for the reversal of the original language. It's that simple. And if we think about non-deterministic finite state automata, particularly from the perspective of these triangular constraint systems, all we have to do is mirror the constraint system, mirror those triangles, and we wind up getting a triangular constraint system for the reversed language. On the other hand, it's not obvious how we could take a deterministic finite state automaton and turn it into a deterministic finite state automaton that accepts the reverse of the language. For the next video, we're going to need some closure properties that might seem a little bit odd initially, but make sense when you think about things in terms of multi-input automata. Remember that if we have a bunch of inputs that we want to input into an automaton, by first padding all of our inputs with octothorpes with end-of-word characters so that they're all the same length, and then threading all of our inputs together so that the first character of the input is the first character of all of the individual inputs, and so on and so forth. So if we have three inputs like this, we can merge them together. First, we take the inputs and we pad them so that they're all of length 4. And then we view this as a word of length 4, where this is the first character of that word, this is the second character of the word, this is the third character, and this is the fourth character. The characters still come from some finite set. It's much larger now, but we can still feed in this tuple all at once as the first input to our automaton, and this tuple all at once as the second input to the automaton, and this tuple all at once as the third input to the automaton. So the first type of closure that we're going to need is called closure under projection. We're going to want to be able to take words that look like this and get rid of, let's say we wanted to get rid of the first characters of all of these tuples, right? That's going to change the alphabet a bit. The alphabet here is triples of characters, or possibly octothorpes, and the resulting alphabet is going to be pairs of characters, or possibly octothorpes. We want to turn this, for instance, into something like this four-letter word. And essentially all we're doing is we are applying some sort of function between alphabets to each of the characters of this word here, where that function is specifically the ignore the first part of the tuple function, right? So we take ABB and we ignore the first part of the tuple and we get BB. So we've applied that function to this first character and then to the second character and so on and so forth applied it to all of the characters to get this result here. It's actually really obvious that we can do this if we think about this from the perspective of non-deterministic finite state automata. Each of the edge transitions of the non-deterministic finite state automaton that's reading in this particular word is going to be labeled with these triples here, characters in these higher alphabets. And all we have to do is apply this function of forgetting the first character to each of those characters. So if we saw an edge like this, labeled with this character, we would turn it into an edge labeled with this character. And that construction actually just does what we need it to do. It does this translation from here to here. You could also think about taking the regular expression for whatever language we want this word to be part of, and simply applying that translation to each of the characters in the regular expression. But there's something a little bit tricky here. Suppose that instead of forgetting the first character of this tuple, we instead wanted to forget the second character of the tuple. Instead of turning that into this tuple here, I'm actually going to want to get rid of these last two characters. And I'm going to want to do that for everything in the language. And so we need it to be the case that we can trim any trailing all octothorpe characters from the end of a particular word. Well, that's fine. This is something that you can do if you think about this from the perspective of even a deterministic finite state automaton. You just move the accept states backwards along these edges so that you don't have to traverse them, and then get rid of those edges so that we don't use this forbidden octothorpe character. So why do we care about this particular type of projection? Well, this particular projection, let's talk about this first projection operation. This first projection operation corresponds to taking a language L that is going to be on this more complicated alphabet, so we can think of it as consisting of not just individual words, but triples of words, right? We can interpret this as this triple of words. Taking a language L that represents triples of words, and then looking for all of the pairs where there exists a word that we could add in as the first thing and get an element of the language. And again, this will wind up being extremely important in the next video. We'll also need closure under expansion, taking words that look like this and replacing them with a large quantity of words. All words that could be obtained in the form of putting some word in as the first word of a tuple, and then having these words in as the second words of the tuple. So that means that not only are we going to have to, if we have this in our original language, when we expand our language, not only are we going to have things like this in our new language, but we're also going to need things like this, where we lengthen our word to accommodate the fact that this mystery word might be longer than the longest word of our original tuple. However, accommodating this sort of thing is actually really simple. All we need to do is have two automata working in parallel. One of them making sure that these second parts of this input here fall into the regular language that this original word was required to fall into, and then another part of the automaton that just makes sure that the whole thing is a well-constructed tuple, that it doesn't have any octothorpe characters, which we're not really going to consider proper, and this first word here doesn't have any octothorpes in it in the middle of it before the end, right? In our earlier example, it could have octothorpe in it, but it can't have octothorpe in it followed by an A or a B. And so we have to make sure that that doesn't happen. But that's fine. That's a thing that you can build an automaton to do. Very simple. You take these two automata, you kind of group them together in the same sort of construction that we did when we were talking about intersection. There you go. You have an automaton that can recognize the expansion of a particular language. And again, why are we interested in that? Well, we want to be able to talk about the set of all tuples W1, W2, W3, such that the pairs W2, W3 fall into some other language, some sort of regular language that we require this original word to fall into. And again, this will hopefully be a little bit more clear in my next video when I talk about regular logics. So that's it for this video, and I hope to see you then.